In this video, we are looking at the fundamental theorem of calculus. Alright, now you've been introduced to two major branches of calculus, both differential and integral calculus, and at this point, you might not completely see how they're related. We have talked a little bit about antiderivatives and integration, but now we're going to get a little deeper when we talk about the area under a curve, which is that definite integration. This connection was discovered independently by both Isaac Newton and Gottfried Leibniz, and it's stated in the fundamental theorem of calculus. Now, informally, the theorem states that differentiation and definite integration are inverse operations, basically in the same sense that division and multiplication are inverses of each other. Now, to see how Newton and Leibniz might have anticipated this relationship, you can look at these two different approximations. We've got the tangent line approximation, and we've got the area of the region under a curve approximation. So we know that the tangent line approximation is roughly dy dx, or delta y delta x, because that's the change in y and the change in x, right? That's the slope. When we talk about area, we're talking about base times height, the approximation of this rectangle versus the actuality of this area, but we can still do it as an approximation, delta y times delta x. So the slope is a quotient. The region under a curve is defined using a product, okay? So at least in the primitive approximation stage, the operations appear to have an inverse relationship, the same as division and multiplication. But the fundamental theorem of calculus states that the limit processes preserve that inverse relationship, okay? So what does that mean? That means this. The integral of f of x from a to b is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. Basically, you're just talking about evaluating it at two different points, right? That's all you got to do. Now, this is all assuming that f is continuous on a closed interval and f is an antiderivative, that you can find the antiderivative. So, let's look at a couple of different guidelines. First thing, provided you can find an antiderivative, now we're going to use this method instead of using the limit of a sum, okay? We've determined that upper and lower limits, Riemann sums, they are, oh my goodness, they're long, they're challenging, they're easy to make mistakes in. So if we can find a different way, an easier way, that's the preferable thing to do. So when applying this, we've got a specific notation we're going to use. We're going to take the function, we're going to take the derivative, take the antiderivative. Once we take the antiderivative, we're going to evaluate it at its upper bound and its lower bound, okay? And we're going to write it like this. You don't have to put a bracket, just put like a bar. A straight line, okay? And that tells us we're going to evaluate it here, and then we're going to subtract it and evaluate it here. An example would be the integral of x cubed. We know to get this integral, we're going to use the inverse, the antiderivative backwards of taking the derivative. We're going to add 1 and divide by that number. So x to the fourth divided by 4. And we're going to put a little line, and we're going to evaluate it at 3, and we're going to evaluate it at 1. So we get 3 to the fourth over 4, minus 1 to the fourth over 4, or just 20. Now, it's not necessary to include that constant of integration. We don't have to put the plus c, because when we evaluate it, because the plus c is just going to be there, if we subtract c minus c, it just goes away anyway, so no reason to put it there. So let's take a look at this example here. So we've got the integral of x squared minus 3 from 1 to 2. All right, so this is not too bad a problem. We're going to separate it out from 1 to 2 of x squared dx minus the integral from 1 to 2 of 3 dx. So here we're going to raise this to the third power and divide by 3, and we're going to evaluate it at 1 and 2. And then we're going to do the same thing here. We've got 3x evaluated at from 1 to 2. So we're going to plug the 2 in, we get 8/3, minus, plug the 1 in, we get 1/3. All right, minus, over here, we're going to plug the 2 in, we get 6, minus, plug the 1 in, we get 3. So we've got 8/3 minus 1/3 is 7/3, minus 3, which is 7/3 minus 9/3, or negative 2/3. Here we've got another one. We're going to rewrite this one from 1 to 4 of 3x to the 1/2 dx. Now we're going to do the same thing we did before. We're going to raise this, add 1, so that's 3/2, We've still got the 3. Now we're going to divide by 3 halves. Okay? Now, we're going to evaluate this from 1 to 4. Now, I don't like dividing by this, so I'm going to multiply by 2/3 times 2/3. So this gives us, the 3's cancel out. We just have 2x to the 3 halves evaluated from 1 to 4. Y'all see how that happened? Okay? So, square root of 4 is 2, cubed is 8, 8 times 2 is 16, minus, plug in a 1, 2, we get 14. Here we've got secant squared x. We know the integral, I don't have to rewrite the integral here. I know the antiderivative automatically is just tangent, and we're going to evaluate it from 0 to pi over 4. So that tells me that tan pi over 4 minus tan 0, but tangent of pi over 4 is 1, tangent of 0 is 0, 1 minus 0 is 1. So if you have any questions about doing these definite integrals using the fundamental theorem of calculus, please just shoot me a reminder or ask questions in class.